So what happens when you have sort of large amount of water and the water try to flow out?
Get like a tornado effect.
Right, so this is what you observe in your sink, right, or in your bathtub. As you have a lot of water, they'll try to go out, you have a whirlpool, right? And the idea is once you have this kind of whirlpool, we can use it to turn a turbine this way. So here you're not shooting water jets at the individual cups anymore. Basically, what you do is you put the entire turbine in water and say, because I have high flow rate, so this whole thing is submerged in water. Water will create a whirlpool effect once it joins anyways. So this will turn my turbine. Okay, so this is called a reaction turbine. This when you use as maybe the water speed is not super high, but then you have large amount of flow, right? And so naturally you have pressure difference across the blade, and this will turn the blades. So these are the two types of turbines. And this is what this reaction turbine looks like. As you lower this whole thing in water, and this creates a rotation in your turbine. Right, so it can look like this, or Kaplan turbine is a different design of reaction turbines, but it's the same principle. And you want to submerge this whole thing in water. And once water leaves will create some rotation, and this will turn your turbine. So these are the two ideas. Okay, so the rest of this class is really to look at. So it turns out for reaction turbines, it's hard to do calculations, but we'll do some calculations for sort of generic, for a more generic hydro plant. Then we'll start looking at impulse turbines. How do we design the shape of the different cups? Okay. So any questions about the two different types of turbines?
There's one question in the chat says like, depend on these two pictures, like the efficiency of it, is that a difference?
Yeah, so that's a reason we use two different types, right? So when you have really high speed, low flow rate, if your flow rate is not enough to submerge the whole thing in water, then you really have to use impulse turbine. Right? You don't have enough water for reaction turbines to work. Okay, so you need to use impulse turbine and you need to direct where the water goes. Okay, that's really where you use impulse turbines for. If you have a lot of water, it turns out to be not very efficient to shoot out this sort of water jets everywhere. But it's more efficient just flow the water in and use a reaction turbine. Yeah. So with the reason we have two is depending on situation, one is more efficient than the other.
So it's depend on the volume and the situation of it. Okay.
Depend on the volume. Depend on the flow rate and depend on the velocity of the water. But your velocity is built up by going through a very high head, right? Going through a large drop. And your flow rate depends on the volume and depends on sort of the flow rate into the reservoir and a bunch of things. It's really dependent on exactly sort of the setup of the reservoir. But the idea is if you don't have enough water, then you need water to have high speed. And that's when you have to use an impulse turbine. You have a lot of water, you can use reaction turbine.
I see.
Yeah. Okay, good. All right, so let's do one example, right, with some numbers to see. There's some typical numbers. So let's say I have a reservoir. I have a flow of 36 cubic meters per second, 70% efficiency, the density of water and the value for G. The idea for this calculation is to get some feeling for the values we can get. So if we look at the electrical power we have here, then this is just 0.7 times 1,000, and at 0.81. So 236. So you multiply everything together, we end up getting as the number 15 megawatts. And this is a typical number for a hydropower plant. the hydropower plants, for most hydropower plants, these are not small plants, right? We're talking about numbers in the tens of megawatts and hundreds of megawatts, right? So these are very large machines, right? So as you can see from the size of the turbines, these are again very large machines. So a typical number is 50 megawatt, 100 megawatts. And if you, right, as a question was asked before, right, if I'm gonna use a impulse turbine, what is the speed of the water that hits a turbine, right? So we want to get an estimate of this speed and see how fast the speed actually is. Right? So if we want the estimate of the speed, then how do we calculate that? How do we calculate estimate of the speed? Right, so we're going to convert, right? We're going to convert the potential energy to kinetic energy. So what equation do we use?
1/2 rho v square.
Equals to what? Right, so we have 1/2 rho v square. This equals to
The 50
Equal to
megawatts, right?
rho
Because it's a constant.
EH.
right. So we can use 500 megawatts, or we can say this is rho gh, right, to give us a ballpark estimate. Right, so let's say this. If we ignore the efficiency, let's see our ballpark estimate for this as V is roughly square root of 2gh. This is roughly 62 meters per second. This 223 kilometers per hour, right? So we have efficiency. If we have a 70, if we have an efficiency of 70%, it's slightly lower, but this is again as a ballpark number of the speed of water you expect to see. Okay, so again, this is fairly fast. This is pretty fast water flow. Right, so this is our speed. Okay. So this is an example of where we have a high H, right? When H is large, we can build up high speed, and that makes sense for us to use a impulse turbine. Now, if we have a low head side, right? So here we want to use a reaction turbine because H is now smaller. Right, so before H was 200 meters, here is 10 meters. So our speed will not be very large. So there's no way we can get a lot of power if we rely on conversion to kinetic energy. Right, so here what we want is we want a reaction turbine. And to get a reaction turbine, what we need is I need a lot of flow rate. Right? I need a lot of water to flow. So let's look at how much water I need to get to also get a comparable power output, 50 megawatt power output. So here the electric power, this is the rho gh times the flow rate, right? This is another way we can compute it. Then if you compute the flow rate, this turns out to be 7.8 meters cubed per second. Right? So again, not a small number. Okay. Right, so this again illustrates a case where, right, so it's really more efficient to use one type of turbine than the other type. You want to, essentially based on H, pick the right one you want to use. Right. So of course, if your H is small and your flow rate is small, then it doesn't make sense to build a hydropower plant there. Right. So we say there's a finite amount of hydro resources. Right, or you often hear the sentence that the US has tapped out most of its hydro resources is because we basically run out of places where either H is large or H is small but Q is large. We don't have many of these places left in the US to build hydropower. Okay, so we've pretty much used all of them. But there's, depending on which case we have, we use different turbines.
So I understand obviously why you wouldn't want low, but are there any situations where it's high? So high volume.
high we have, but high normally turns out to be more efficient to have many turbines instead of few large ones. So yeah, so the best place is high head, high volume. Then what we do is we have a lot of turbines. It's more efficient to build many ones than say some super large turbines. So really, if you have high height, then what we do is we have many penstocks, right? And you have say 20 turbines in parallel. That's a more common situation.
So in that situation, would they use reaction or
Impulse? Impulse, yeah. Okay. So I think, yeah. So I think, for example, Hoover Dam is like that. When you have sort of, when you have high height, you have a lot of flow rate, it makes sense to divide them up. Right? And later in the class, by the end of the class, you'll see, right? So one consequence of having large numbers, right? Have something, that's moves at hundreds of cubic meters per second at, hundreds of kilometers per hour. We'll see as what happens when things go wrong, right? Similar as wind, right? We saw what happens when things fails. Later in the class, we'll see, if things fails, really fail quite catastrophically, this kind of thing. Right? So this is also something to keep in mind, hydropower. All right, so then next is, let's look at turbine design, right? So next really is the sort of interesting engineering question. Let's say I want to use an impulse turbine. So let's say I'm at a large H setting. Right? I want to capture most of the kinetic energy here. Right? So this is showing this figure again, right? Right? So how do I design the cup? Right? So the question is, design this. Okay, the idea is you want to design this cup, the shape of this. And turns out, our design of the cup is actually look like this. So we do not, right? So what we do not do is this is not, so it's not something like a convex shape. We actually don't design it like a convex shape. What we design is we have this sort of hitch in the middle. Right? We have this sort of hitch in the middle. So why is that? Right. So when you look at most of the turbine designs, you see this hitch, where we see this kink in the middle. Why not just design it as a convex shape? Why bother with this kink in the middle? Any ideas? What's wrong with this convex shape?
Because that would increase the speed faster.
No, speed is good, right? Larger the speed is good, right? Power goes, V squared. The larger the speed is better. Right? The problem with the convex shape is actually not the speed is smaller. But why would the speed be smaller, say for the very smooth convex one compared to the one with this double cup design? Right, so think about what happens if I shoot a jet of water here. If this is simply a convex shape.
It'll just reflect back.
Right, so what happens is this just bounces back. Essentially what you have is if you shoot a jet like this just bounces back. Okay? So this reduces efficiency because your water hits it and everything bounces straight back. And this cancels some of the incoming water. Okay, so this is the problem with something like a mirror, right? So if you have this sort of convex mirror, something hits it, gets reflected back, and that's not good if you have additional water coming in. So the idea with this sort of double cup design is if you have an incoming jet of water, the water that bounces back goes along the cup and goes out the side. So the water don't cancel each other out. Okay? So you don't have water cancel each other out. And this gives you a much better efficiency compared to what you would expect naively, this kind of shape.
For the shape on the right there,
Yeah.
why can't you just shoot the water to one side of it instead of down the middle? Would that limit the amount of kind of reflection of the water?
That will limit it by shooting at one side. It's hard to do, right? So it's hard to sort of aim at that, right? So you can shoot one side of it, but that's still not as efficient because you create some direction that's for not pushing it all forward, but pushing to the side. So what happens is right? So all these are attached to a rotor, right? So if you have this, you shoot one side of it. What you want is you want all the force to go this way. But you shoot toward the side, a lot of force is not going to the rotation speed. It doesn't rotate the rotor faster. That right?
Yeah, that makes sense.
Yeah, right. So you want to basically shoot it, right? So what you want is you want the force to go this way, right? If the rotor is here, you want the force to go this way, and you don't want the water to bounce back at you, right? So you don't want the water to bounce back. So what you want is this is the sort of the double cup design. Turns out to be a good design. So again, if you have a lot of water, this doesn't make a difference. There's water everywhere. But this again, this shows you if you don't have very large flow rate, and the jet you have is, it's fairly narrow jet, it's fairly defined, then it's good to design the cup this way. All right, so now basically what we want to do is to figure out the energy transfer. It's just a momentum balance. We have some incoming momentum from the incoming water jet. We have some water that's leaving it. Right? We have some momentum transfer to the speed of the cup. So that's what we want to see is exactly how the momentum transfers. Right? What is the net momentum we get, and how much momentum and therefore power is transferred from the water to the cup. So that's a transfer power from water to the turbine. So if you look at different momentums we have in this, right? So we have what we call MA. This is the momentum of the incoming water. Okay, so this momentum of incoming water. So what we have momentum is, we call this as M times V. So here MA, this is the mass of incoming water times, now what is the speed of the water? Right, so what, right, so we can use VI, but there is a better reference to use. Right, so if you think of this situation, you have water hitting the cup and the cup rotating, right? So what reference should we use actually in this?
VC.
Right, we will reference everything to VC because VC, we're really hitting something that's moving at the speed VC. Okay, so for the momentum calculation, it's easier. We reference everything to VC, or it's more symmetrical, reference everything to VC. Okay, so here what we'll do is we'll reference to VC, right? Because the cup is moving, we're hitting this moving cup. So let's make this reference, right? So let's make this reference. So this is VI minus VC, right? So VC is moving this way, we have VI coming in. So the difference in speed, right? So our momentum is really the mass times the difference in the speed. Right? So again, because of VI exactly equal to VC, there'll be no momentum, right? From the cost perspective. Okay. All right, so if we take this as a reference, then let's look at the reflected water, right? We have, two sort. We have a incoming water, we have reflected. So let's say R, this is the momentum in reflected water. Okay. So this is really mr. This is again the mass. Little m r. And now what's the speed? This is VR. How does VC enter here?
Plus VC since it's different directions.
Right, so this is plus VC, right? They're going in different direction. So this is plus VC. Okay, so we have minus VC for the incoming water, plus VC for the reflected water. Any question about this?
Wait, I'm kind of confused with the bottom formula, the MR.
Right, okay, so MR, right? So little mr is a mass. We have the reflected water going at a speed of VR. Okay? And we're referencing to VC. So VC is moving to this direction. VR is moving in the opposite direction. Okay, so if we look at the speed reference to the speed of the cup, then we need to add the speed of cup to it, right? Because they're moving in different directions.
Okay, thank you.
Right, so yeah, so we're reference to a moving cup, right? So if we're bouncing back from the moving cup, then we need to add a cup speed to it. So this is our two momentums, right? So our momentum, this is what we have. So then if you look at the changing momentum, right, we have incoming momentum, we have momentum that's leaving. So really, if you look at the change, the delta momentum, this is the momentum we get, or this is momentum captured by the cup. It's just a subtraction. We'll make simplifying assumptions. We'll assume the mass are equal, right? So the amount of water doesn't change. We'll assume that the incoming speed, right, the reflected speed is equal to the incoming speed. So this is simplification, but will give us a sort of simple formula that's roughly correct. So this is delta M. If you subtract these two, what we get is 2m VI minus VC. Okay, so it's twice the mass times the difference between the incoming water and the cup speed. Right, so this is our transfer of momentum. Any questions with this equation? Okay, so this is the momentum captured by the cup. Our next step is simply sort of convert the momentum to power. Right, we want to convert this to power. So let's see how we come. So any ideas? How do we convert from momentum to power? Anybody remember this conversion? Right, so we know the net momentum captured by the cup is 2mi times the speed difference. And what is the power captured by the cup? And so, okay, so review for equations, right? So anybody remember how do I convert this to force? Yeah, how do I convert momentum to force?
Isn't momentum just a derivative of force?
Good, right? So here we'll take an even simpler equation. We'll take momentum to force to be momentum divided by t, right? So this is 2mi t vi minus vc. How do I convert force to power? So I know the force exerted on the cup. How do I convert this force to the power I'm generating on this cup?
If we have a distance, we could use work, force times distance to get work.
That we have a simpler formula, right? So we don't know the distance, but what do we know? All right, so this
We know.
right? So force times speed, right? Power is force times speed. Where the cup is moving at a speed of VC. We know the force, the power is force times speed. And this gives us 2mi over T, Vi minus Vc times Vc, or equivalently, we will write this as 2Q rho Vi minus Vc times Vc. Because I'm I over T, the mass over time is equal to the flow rate multiplied by the density of water. So since flow rate is something that's much easier to measure in practice, so more often when you'll see this equation. And we can measure the flow rate, we can measure different speeds, then we can talk about the power generated based on the flow rate, the density of water, and the difference in the speed and the cup speed. Any questions about this equation?
I'm a little bit confused with the force. It's the derivative of the momentum over time, because this is the first time I see.
Oh, really? Okay. Yeah, so you should have seen this in physics, but normally force is the
Maybe I forget it.
yeah, so it's momentum divided by time. We're not gonna use the derivative. We're gonna assume sort of constant momentum change. So momentum divided by time is our force. I'm not sure. I guess one way you can think of as a unit lines up, right? So force is ma, right? It's mass times acceleration. F equals ma, Newton's second law. So you can think of momentum as m times v. So the time derivative of velocity is acceleration. So force is F, right? It's the momentum, time derivative of momentum, assuming a constant mass. Right? You recover F equals ma. I think as John is saying in the chat. So here, assuming constant momentum transfer divided by t, essentially recovers Newton's second law.
Okay, gotcha.
Right. Any other questions about this? All right, so if not, let's take our break. So let's break for 10 minutes until 3:32. Then come back, we'll do some exercises based on these equations. We'll see some more numbers. Okay, so otherwise, we'll come back at 3:32. Sorry, we'll come back at 3:32. All right, so let's come back to this. Okay, so this is our equation. All right, this is our equation. I'll type down here. So just let's do a simple example to compute what the numbers are. Okay, so if you look at this question says a cup receives 10 cubic meters per second of water. The speed of the cup is, we're going to fix this at 200 meters per second. Then we want to control the speed of the injected water for the power captured by the cup to be 40 megawatt. So here we have P is equal to 2Q rho Vi minus Vc times Vc. So here we have Vc as 200 meters per second fixed. So then we can solve for Vi, and what we have is 4 times 10 to the 7, 40 megawatt is 2 times 10 times 10 to the 3, Vi minus 200 times 200. So you get Vi as 210 meters per second. Okay, so that's a sort of type of question you'll see, right? So during the homework, you may see something, or the exam, you'll see something either given the cup speed or given the you're given either VC or VI, and to solve for the other one. So if given VC as a linear equation, given VI as a quadratic equation, but obviously you should pick the positive value for VC. Right? So this is the sort of governing equation we have for the impulse engine. Okay, so this is the impulse engine. We're going to use this kind of simple equations, but then for something like reaction engine, equations are hard to derive. it's really hard to get an accurate picture of this. So here I'm showing you a simulation of what happens. Right, so you see water flowing from top to bottom, and then as water drains out, this turns the turbine. Right, for this reaction turbine, what we actually do is you see a lot of simulation, right? This sort of fluid mechanic, this sort of really fluid simulations to calculate the exact power transfer. So here we're going to look at the principles behind this, but maybe not going into so much detail of the equations. So we won't get a equation as clean as this one, where everything is measurable. That's a good thing about equation like this. You can measure all the quantities there. You can measure flow rate. We know density. You can measure VI. You can measure VC. Okay, so these are all measurable quantities. But for reaction, a little bit harder to get things that way. Right? But we can look at the operating principle behind it. Okay. Principle behind, and the principle is still conservation of energy, right? What this thing still is, even though you have this sort of complicated dynamics of water, flowing past the turbine, flowing past the blades, but still the idea is if this is your blade of the turbine, then some energy at this side is the energy that's coming before the blade is dividing into the energy captured by the blade and the energy of the water past the blade. Right? So this is our conservation of energy. And then here for reaction, we're going to assume that, right? So the turbine is entirely immersed in water. Okay? So here the entire turbine is in water. Okay? So here we have, both the pressure energy. Right, this is sort of water pressing on the blade. It's pressing downwards. You can think of water pressing downwards on the blade. There's some pressure energy. And then you have this kinetic energy, right, of the moving water, of the moving mass of water, both of these. Okay, so we have these two energies, and we're going to try to do an energy balance. So we're going to do energy balance, looking at the energy just before the blade, and looking at the energy just after the blade. So before the blade, our energy is the pressure energy before times the volume, how large, right, how much water we have, plus 1/2. Speed, this is pressure times volume, plus half, missing M. Okay, so this is before and after. And the energy transfer on the blade, this is E1 minus E2. And this, the energy we get on the blade is the pressure difference times the volume plus the mass times the square of the speed difference. Okay, so this is the equation we get by looking at before and after. Then if you look at the reaction turbine, right? So since this whole thing is entirely immersed in water, do we anticipate a large speed difference before and after the blade? Was the speed change appreciably before and after the blade?
No.
No, right? So this whole thing is in water, and the water is incompressible and all that. So the speed is actually, this is roughly 0. Okay, we don't need to look at this because we have similar speed. So we'll make one assumption as V1 equals V2. So we're going to kill this term. Right. And then another assumption we'll make is we'll make the assumption that pressure on the other side is very small. So what this says is the pressure on the other side of the blade is small. So then the energy is basically the pressure on one side of the blade times volume. And power is energy divided by T. So this is just the pressure times the flow rate. right? Pressure times flow rate. But we won't be able to get any more explicit than this, right? So the best we can get is, some pressure times the flow rate. The difficult thing here is flow rate is something we can measure, but pressure is harder to get a handle on, right? So it's harder to get a handle on what exactly is the pressure of the surface of the blade. That we typically don't know. Okay, so this is more of a conceptual equation than say, something we can plug numbers into. Okay, right. So this is as far as we'll get there. If you're interested in this kind of turbine design, there really is, you need to learn a lot more about the fluid flow. And then often it's basically done in this kind of simulation, right? We need to really simulate the flow in a reaction turbine. And yeah, go ahead.
So if pressure makes up is that much of a difference in these things, would that mean that these things are less efficient? Because obviously more pressure means more friction when turning the turbine now.
Right, so that's why you don't have 100% efficiency, right?
But I'm saying are reaction turbines less efficient than impulse, or are they roughly the same?
Roughly the same. You can design if you pick the correct kind of turbines, you both get about 60% efficiency. Yeah, they're not inherently less efficient. When the H is low, that's sort of the only choice you have. And the impulse turbine, there are also many sources of loss, right? So you have water heating it. Of course, some water will bounce back and cancel each other out. You don't hit the correct target right on, things like that. So it turns out roughly to be similar efficiency. Yeah, so you have losses, right? All this sort of ignoring loss, but that's why we have this sort of catch-all efficiency. That's about 60%, 70% efficiency. Good question. Okay, so this is the equation we'll get to. It's sort of not very interesting equation. So more interestingly is to look at different kind of hydropower we can have. So there are actually 3 types of hydropower for us. Okay? There are actually 3 ones that you commonly see in practice. So impounded hydropower means the hydropower plant you have in your mind. And this is where you have a large reservoir, you have a big dam, right, like the Grand Coulee, and you have, this is what we think of as being hydropower. Divergent hydropower, this is different. This is more of a run of the river. So when you build a hydropower plant, often as what you need is you need to build a reservoir. That means you need to build a lake, basically. But for a small river, it doesn't make sense often to build this kind of large reservoir. What you do is run of the river is just put a turbine in water, right? So running water will turn the turbine. So let's just put a turbine there to generate some electricity out of it. And this you actually see in the state of Washington. So Bellevue, or not Bellevue, Puget Sound Energy have some divergent hydropower. But you find some small river, just put some turbine across it. And then we'll look at sort of pump hydro storage, where you pump water back up the hill as a form of storage. So if you look at impounded hydropower, then this is just where you build large reservoirs. You have, reasonably high head. Doesn't have to be hundreds of meters, but should be more than a few meters, so reasonably high. And you can control the electric output by controlling the flow of power, flow of water. So this is really controlling Q, controlling the flow rate. So what you have is have a valve on the penstock where the water is flowing from. And by opening and closing this valve, we can control Q. And this controls the electric power. And these are the large power plants like Grand Coulee. Right? These are sort of really large ones. So you want to have a look. This is Grand Coulee, right? So where you have a lot of generators, you have a spillway. And so if you zoom in for each of these, each one of these has a generator. All these have generators coming down here. Okay, so this is the sort of quintessential example of a large hydropower plant. So this is in our state. And this is again really, really large. The idea here is these power plants are gigawatt level plants. They're really large. And right, so they have large generators in them. Okay, so this is a picture of the generators we have. And this are some data we can look at. Right, so what we'll do, we'll compare against sort of the largest hydropower plant we have in the world, Three Gorges Dam in China, with Grand Coulee, which is the largest in the US. Okay. So if you look at this as, right, so, both roughly have the same height. Right? So they're roughly the same height. The difference is just that the reservoir behind Three Gorges is much, much larger than the reservoir behind Grand Coulee. Okay, so when people build Three Gorges power plant, they build a huge reservoir. Okay, they build this, and it's a really big reservoir. And so if you look at that as a judgment of size, it's much larger. Okay, and so we can think about it. If you build a hydropower plant, right? So why might you want to build a huge reservoir? Right, so for Grand Coulee, we built a relatively small reservoir. Or for Three Gorges, engineers built a huge reservoir behind it. What might be some of the reasons behind
that? They want a larger volume and there's space available for it.
Space is debatable, right? So you can do something else with the space. Really, so you don't build a large reservoir for no reason, right? You don't want to flood, other spaces. But there's good reason to build this.
Annual rainfall. I have no idea where the Three Gorges Dam in China is, but obviously Seattle gets a lot of rain a year, so replenishing it's not that hard.
Right. So what this reservoir? So this actually hints at the functions of the dam, right? For us, for this class, all we've been talking about is generating electric power, right? So a dam is basically something that generates electric power for us. So what else does the dam do? What else does, what other reasons will you build a dam?
Regulate water flow downstream.
Regulate water flow, right? So flood control and agriculture, right? So for irrigation and flood control purposes and power generation. So which of these comes last? Irrigation, flood control, and power generation. Which of them are the least important one?
Power.
Power. Power is never the first priority. So hydropower. So hydropower scheduling has its own very interesting quirks to it, because hydropower in some sense is very controllable, right? I get to control, right? So if you look at Grand Coulee, basically you have a lot of freedom how water flow can flow through this site to generate power, or you can spill water this way. So in some sense, this looks like an extremely controllable generator. But often the dam is trying to do other things, and they have much higher priority than, say, just generating power. Right? So scheduling is, you cannot exactly take hydropower to be this resource that does whatever you want and can ramp up and down. Right? Often you have constraints that doesn't have that much to do with electricity, but has to do with other functions the dam is trying to serve. And so that's something pretty particular to our state. So for some other state that doesn't have hydropower, it doesn't enter into the picture. But for our state, especially if you go work for Puget Sound Energy, and you get, or you work for Bonneville Power Authority, you'll be thinking a lot about sort of scheduling around the other functions the dam has to serve. And so that's something to be aware of, as dams are normally serve many purposes, and electric power generation is not the highest priority for this. Okay. So Three Gorges Dam really is a big part of this flood control. You need a huge reservoir because you want to do flow control. And then this is just comparison, but now we're going to look at the electric capacity. So Three Gorges is the largest, so by far, in the world, but there are some pretty large ones. There are pretty large ones. So we have a largest one in North America, in US and Canada, but then there are some larger ones in Canada. So these are the large hydropower plants we have in the world. Right. So for this hydropower plant, there's environmental impacts, right, for this hydropower plant. So when you have a large reservoir, so for this large power plant, you need a reasonable sized reservoir, even for ground cooling, right? It's much smaller than Three Gorges, but still not that small. When we build a large reservoir, this displaces population, right? Somebody has to move. And this, destroys landscape, right? It destroys, you're flooding this underwater, whatever you had before. And again, for us, this is actually an important part, river ecology. For state of Washington, this is important because this kills the fish. And for us, this is very important that you don't operate to impact the ecology. Right? The ground cooling has to have this constraint. Some time of the year, you're constrained by sort of the other needs we have in the river. Right? You don't want to kill too many fishes in the river. So what we have is sort of very unlikely to see large dams in the US. Okay, so it's very, very unlikely we'll build something in the gigawatt range again. Right? We pretty much built at all the places we could have built dams. Okay, so even though hydropower is renewable, right? It's renewable, it's clean, it's very well understood technology. The trouble is you just won't be able to build many large ones anymore, at least in the US. Any questions?
I'm kind of surprised not to see the Hoover Dam even on that list. Do you know what the capacity of that is?
2 gigawatt, I would guess.
Wow, that low, huh?
Yeah, Hoover Dam was famous, right, for being early. We started building larger and larger ones after that. It's a very important proof of concept, right, for that. But after that, we got very good at building super large dams.
Is that just because of the turbines they have in there, or just the place that it's built?
No, concrete, right? So these dams, you need to use concrete. And so what happens when concrete sets? When you pour concrete to build a dam, what actually happens to the concrete?
It keeps getting harder and stronger over time.
Harder and stronger, but generates heat, actually. It warms up.
Right.
So actually a big part of building this is, right, you need to pour concrete, right, once you build a dam. How do you get rid of that excess heat was a major engineering challenge for large dams. Or just getting rid of that. Right, so that we need to know how to do. So we keep figuring that out. Is how do you do that? So that's one practical challenge we have. Second is, just we need to build larger turbines, although not that much larger. Just for the skill, the engineering skills, we got better at building skills, right? Building these large things. And 2 megawatt to 2 gigawatt to 20 gigawatt is not that large of a jump compared to something like wind. Wind went from tens of kilowatts nowadays to tens of megawatts. So a 1,000-fold increase. Hydro is, we start out pretty big and we got an order of magnitude larger, but still roughly in the same ballpark. Yeah, so these are large things. So if you have a chance to visit any of these, I highly suggest you visit. But you really get an idea of the size of these things. Right? So understand why it's hard to build any more of these. Right? So it's just really large. So if you run out of the chance to build large dams, what you do is you build small ones. Right? So this is where we're starting to build. We're going to build run of river. Okay, so this is basically you have a river, put a generator across it. There's no reservoir. There's no reservoir. There's no flow control. But this is sort of small, or even sometimes, no noticeable environmental impact. You pick a small river, it really doesn't have that big of environmental impact. So you'll see some effort nowadays to build divergent hydropower. But the most difficult thing for this kind of power plant is this: you don't have any flow control. So it's very hard to forecast. Right, so you don't really know sort of the volume or the flow rate of a river. And it's not easy to forecast this. So that's a challenge. But these are the hydropower that we're building nowadays, the hydropower plant we're building nowadays. So we look at an example. This is, right, so you have a water coming in, you build a penstock, you build a turbine, and this runs beside the river for a while, and you generate power this way. Okay, so it's really simple technology. And this is one example you'll see. Right, so in practice, looks something like this. Right, and you see, and sort of Snohomish PUD is building this. So something close to home, Snohomish PUD is trying to build the 5 megawatt generators because they have some water with relatively high head. Right, not very large flow rate. It doesn't make sense to build a reservoir, but because it has fairly high large head, then they try to build some round river power plants. So these are, right, so that's, I think they're operational now. So some of our power comes from, if you live within the area, some of power comes from these round river power plants. Right, any questions about these sort of smaller power plants? Okay, so the last thing sort of hydropower, hydropower is pump hydro. Pump hydro is a power plant run backwards, basically. Okay, this is all reverse the direction of water flow. So what you do is you have 2 reservoirs. Really, there is not a river coming in. You're basically flowing water back and forth. You're flowing water back and forth from the lower reservoir to the higher reservoir and vice versa. And the point of doing this is really to use this as a storage device. Okay, so think of this as a big battery. Okay, this is really used as a storage device. And today, the only kind of large scale storage we have is actually pump hydro. Okay, so most of the long-term storage we have in the grid are coming from sort of this large pump hydro plants. Okay, so these power plants will pump water up and downhill. And of course, it's not 100% efficient, but this is the ones that we can make large. Okay, so, and the scale of this is for something like in the gigawatt range. Okay, we'll build pump hydro plants in the gigawatt range because water basically has a very high density. Right? So it's a heavy substance. There stores a lot of potential energy. And the example of this is what happened, right? So this is a Georgia pump hydro picture. This is a lake. Sometimes it's man-made. Sometimes you have a lake that you can pump. There's a difference in reservoirs. There's high difference. You pump water up and down, right, to generate electricity and use this as a storage device.
So these lakes are all man-made, right?
Not all man-made. There are some natural ones, but a lot of them are man-made. A lot of them. You need some sort of, okay, you cannot make this lake again arbitrary, but often as you find when you have a relatively flat hill and the river running below it, that gives a good location. to make a lake and have pump hydro.
I see.
Yeah, so you
So
need
is
to
this-
pump some. Yeah, go ahead.
Sorry, so is this is this an example of something that they would run when you were talking about those times when they're quote unquote paying you to take power? So they kind of run these during those times to burn off the power as well, or
Yes,
not necessarily?
yes, you make money. Yeah, make money. Yeah. So they'll run this, right? When they're paying you to take power, they will run this, for example, if they think there'll be a period of very high demand, then they will generate some extra electricity ahead of time and then pump water up to store this energy. So both happens. So these ones are normally sort of large scale and utility run. So they either, when the price is negative or very low, they'll pump, or they'll forecast as a very high demand coming and they'll pump water up the hill. Yeah. Right, so this is really storing energy in potential energy. So we're going to store potential energy. Right, so pump hydro is really sort of flexibility, right? Gives us flexibility. This is the only way we have to economically store a large amount of power. Turns out we don't really have other ways to do this right now. Okay, so this is the only way we have to do it. Okay, so for pump hydro then, so again, pump hydro only makes sense if you have water to pump and you have landscapes that's fairly favorable to constructing this kind of reservoirs. So nowadays you're seeing people pump all kinds of stuff, right? So there's proposed design in Las Vegas pumping sand. And so moving something up the hill as a form of energy storage. So you move something up the hill. The challenge for things that's not water always come down to how do you turn the turbine when you want to generate electricity, right? So for water, is naturally water will turn the turbine. Sand turning the turbine can create problems. You can't pump sand if you're in Arizona or, right? But then turning the turbine is not easy. And nowadays people are proposing moving all kinds of stuff uphill. The question is, eventually when you move them downhill, how do you turn that into electric power? Right? How do you generate power that way? So there are some crazy designs. So people moving, large blocks of things, large block of stones and things like that. You see some companies trying to explore this area. Right? Well, to pump hydro when we have water, often we don't. Then we need to pump something else. Okay. All right. So and again today, if you can do pump hydro, this is much more economically efficient than say building a lot of batteries. Batteries are not quite there yet compared to pump hydro. So if you look at batteries, of course, if you cannot, batteries are still much more efficient than if you don't have water. But a lot of pushing batteries, you see, how close to pump hydro can we get? If we want to use for large scale batteries instead of building a reservoir. Okay, so this is pump hydro. And then to finish the class, as I promised, we'll look at what goes wrong. Right, so things do go wrong in hydropower plants. And when things go wrong, things go really wrong, because what happens is things go really wrong if you cannot release energy. Right? If you have water, large amount of water, they carry energy. This energy has to go somewhere. So if it doesn't go into as electric energy, it has to do something else. And this is where things go wrong. And this is common for all storage and all power generation. Okay, so this is the example. In Russia, this is a very large hydroelectric dam in Russia. Okay. So it's operating, and I got this online from these folks. As if you look at this hydroelectric power dam, what happens is They have 10 Francis engines, each being a 650 megawatt. Right, so this is a huge rated power dam. This has huge rating. This is, large generation, large turbines, large dam, and so on. So this is a picture of the dam. Right, you have the penstocks. These are where the water flows downwards. You have turbines sitting here. This is your spillway, and you have your control building here. Right, so reasonably, this is a ideal looking place. So this is just picture from the side. And this is what the room should look like. Right? This is what they should look like before the accident. And then what happens after the accident looks like this. Okay, so after an accident, this turned into this thing. Right, so you can see, this air oil tank survived. Most other things didn't survive. You can pick out, what was unit 1, what happened to all these things. But this is what happens after you have accident. When you have accident in this large power stations, it really wipes most of the things out. It's a really catastrophic accident. So, and as you go inside the room, it looks something like this. Okay, it looks, not much survives after this accidents. So any guesses on what happened here? Like what do you think caused this accident?
The dam broken.
So if the dam breaks, actually water goes something else, right? So you have spillway and you have, this is really, the dam didn't get destroyed, right? The dam is still here, it looks fine. It just my units all got destroyed. So what happened here?
The turbines blew. They exploded.
Right, so what caused my turbine to explode?
They over-generated.
There's no such thing. Over-generation does not cause explosion, right? Over-generation means, what, you're generating too much energy? That doesn't cause explosion, right? I don't have, yeah, go ahead.
Did one of the turbines get out of alignment? I'm guessing it wasn't spinning perfectly around, and so it exploded and shattered everything.
Not quite there. Not quite.
The vibration of the turbine and
Not vibration. This is not a resonance that blows things up. So we typically don't have resonances in this kind of turbines. Right. So what caused? So people want to guess, right? So of course, after this, you try to figure out what's happened. You sort through this wreckage and figure out what happened. So the guess is what happens is, so you have all these valves, right? As I mentioned, you have each of these penstocks, right? So have a valve inside the cross section here. You have this kind of valve that coordinates water flow. So their guess is somehow this valves and gates shut off suddenly. You have to shut off, but then there's too much water coming in anyways. So this got punched through, shut off too suddenly, it didn't shut off successfully, and this whole valve gate got destroyed. There was too much water coming down, and that just blew out the turbine and then flooded the entire powerhouse. Right, so then just destroyed everything. Because the water flow was not regular anymore, you blew out the valve and the control mechanism, and the other turbines wasn't controlled correctly. You basically took out the feedback controller that was in the hydroelectric dam, and everything else just blew up, right? Because there's no, it's hard to do, you cannot do speed control anymore. Okay, so the whole thing blew up after a while. And 75 people died, people who work in here died. So this is an example of, again, similar to when the control is important, right? So when we get to synchronous generators in probably 1 or 2 classes, often we'll say, watch frequency, stability is important, stability is important, stability is important. The reason is if things go unstable in our system, it's really things blow up. If things really go unstable, right? It's not, if your car goes unstable, it stops or something like that. As for us, if things goes unstable, something blows up. And this example of a hydropower plant blowing up. Right. So whenever you have things of this size, there's a lot of control mechanism designed into it. Right. So the control is very important. And this is an example of basically a software, the control that was went wrong and destroy the entire plant. Okay, so this is an example. All right, so keep this kind of picture in mind when we get to synchronous generators, because we'll say that people are very conservative when we offer a synchronous generator, want to stay far away from the stability limit. And typically people will question you, why don't you just offer a little bit closer to your safety limit? Why is it that important to stay below it? There's a picture of what happens when your stability goes wrong. When your control goes wrong, this is very bad things happen. Right? So for large power plants. Okay, so I'll stop here today. And next class, so we'll have finished our generation technology. The next class will try to get closer to how generators work. Okay, we'll try to get closer to how generators work. We'll start by looking at something called the three-phase system. And after that, we'll start looking at how exactly does a turbine generate power? How does a generator work? Okay. So reminder, so homework, right? So tomorrow night, you can do the first 3 questions if that's what you want to do. Then I'll see you next Monday.
Thank you.
Thank you, Professor.